The information economy has arrived. The world is teeming with innovation as new business models reinvent every industry. Inside Analysis is your source of information and insight about how to make the most of this exciting new era. Learn more at InsideAnalysis.com.
InsideAnalysis.com.
And now, here's your host, Eric Kavanaugh.
Oh, yes, ladies and gentlemen. Welcome to the future indeed, the future of processing. Yours truly, Eric Kavanaugh here on Inside Analysis, the only coast-to-coast radio show all about the information economy. And folks, what a fantastic show we have lined up for you today. We don't often get to do big product launches, but this one is pretty darn big. So in the computing world, of course, you have processors. The processors are like the brains of the computer. And for the last, decades, 2-3 decades, we've been dealing with something called Moore's Law. And Moore's Law, this is a very interesting concept that says every 2 years or so, you can double the number of transistors on a chip, which means you can basically double the speed. Well, Moore's Law has arguably hit a bit of a wall, but there are other ways to do that. And we're going to find out about that on the show today. We're going to talk about acceleration and how acceleration on processors can really speed things up for different kinds of workloads. So what is a workload? A workload is basically what the computer has to do. And it's very similar to the workloads in your brain. When you're trying to remember something, you're trying to process numbers in your head, right? You have to go through certain processes and you learn how to do that. Well, in the labs, the smart people who work at companies like Intel have figured out ways to optimize not just these more transistors we've been talking about, but now there's a separate kind of thing called an accelerator, which is on the chip itself, custom made for specific kinds of industries and workloads, which is very interesting stuff. So we'll hear from our good buddy Yves Mulkers of 7W Data, and we have Gary Brown from Intel on the show today to talk about what is happening here and why it is such a big deal. And folks, I think everyone just knows no one likes a slower computer, right? Have you ever had someone say, no, I'd like to go ahead and slow down that computer? We're all addicted now to speed. Facebook actually has some credit here because in their design, they really focused on very snappy results. So when you click on something, they know you want to see the results right then. So the cloud has really kind of trained us to expect speed. And now when we don't get speed, we don't like that. No one likes to experience that. I come from a pre-production background from decades ago where you would have to do Photoshop and all these heavy-duty processes and algorithms. You'd run filters on images and you'd hit the enter button and wait an hour, 2 hours. Sometimes they hit the enter button and come back on Monday and hope it all went through. Well, that's the kind of thing these new faster processors can solve with acceleration. And with that background, Yves Mulkers from 7W Data, I get all jazzed about this stuff. I think you know, and I think you do too, because you've been around for a while doing this stuff. This is a big deal, this launch. What do you think, Yves?
Yeah, exactly. It just struck my mind. I mean, looking at things, doing more with less, that's the kind of feeling I got with the new launch of the Intel Xeon processors. A different architecture that helps in really having focused workloads tackled and getting that improvement and power what we are looking out for these days. If you look at traditional CPUs, they were kind of designed to tackle all kind of workloads. And if you had to do a specific workload, like you said, Eric, for word processing or for graphical processing, we needed different other CPUs that collaborated in a certain way to get to this power. And this is what I understood Intel now achieved, to put it all onto one chip. And with artificial intelligence behind the scenes, they can switch depending on the workload and have that architecture do more with less. And a big advantage as well, to my belief, is having more space in the racks and optimizing that to do other things with the space that becomes available in data centers.
Yeah, and there are different kinds of processors. Real quick, you've got, of course, the classic GPUs, but there are also these graphics intensive processors, CPUs, and then TPUs. Even Google came out with. So there are lots of different processors, and we're going to talk today about the Intel processors with these accelerators. And to do that, let's bring in Gary Brown from Intel. So you must be pretty excited to see your baby come true here and get on the market. What are your thoughts on how we got here and what makes these accelerators so special?
Yeah, thanks so much, Eric. Great to talk with you, Yves. Really great to be here at the cusp of the launch of our 4th generation Intel Xeon processor. It's really exciting because the data center, the network, edge computing, whether you're talking about computers that are on premise, doing industrial automation, or in a retail store, or you're talking about, getting online and shopping and e-commerce and digital media and social media, everything people expect from the cloud, there's just more and more compute that's demanded. There's just an insatiable appetite for compute, and it doesn't come for free. And that's why it's so exciting, is how do we trade off compute with cost, with latency and performance and all of this stuff. It's really, really exciting to be a part of the computing era right now, as it's changing and evolving very, very quickly.
Yeah, and let's talk about what these accelerators do, because what gets me excited is this new architectural approach to processing, right? So we understand, I think most people understand, that processor is on the motherboard, it is the brains, the information comes in through the processor, and the faster you get that to go, the more stuff you can get done. But these different workloads are different in nature. Artificial intelligence is different than graphics processing, for example. Cloud computing to support social media, these are different kinds of workloads. Can you explain what an accelerator is and how it works and why it's important?
Yeah, no, that's a great, great question. What are accelerators and what is accelerated computing? But to start to answer the question, I have to back up and talk about the CPU itself, because a lot of people think that, oh yeah, CPUs, they're all the same. They're not the same. They're architected differently. Different companies have different purposes. At Intel, we try to span a very wide number of applications that people want to run, like we said, from the cloud to the network to the edge computing on premise. And in order to talk about accelerators, you have to first imagine that nowadays, building CPUs, you're actually embedding small CPUs into the processor. So you have these embedded CPUs as a part of the overall chip. So if you have a big Intel Xeon chip, it actually has dozens of CPUs on board. And those CPUs are general purpose, they're high performance, doing all kinds of workloads, like you said, from AI to storage to networking, high performance computing. And as in the last few decades, the trend, what the architects have been able to do is, by adding more CPUs to the chip and by cranking up the clock speed of those CPUs, we're able to get more and more performance. And it made a lot of sense. And as our process technology at Intel, we're innovating all the way from the transistor level all the way up to the architecture and the software. So what we've been able to do is tune the software and down all the way to the transistor at all of the different levels to be able to get more and more performance. But the amount of performance improvement that you can get per watt of power. So in other words, in order to hold the same amount of power, in order to get the same amount of cost plugging your computer server into the wall and get more and eke out more and more performance, we've kind of run out of steam on adding more CPU cores, because you can add double the number of little CPU cores into the chip and get double the performance. Great, that sounds fantastic. But guess what? Your power just doubled. Your bill at the end of the month for running your data center just doubled. You can't really do that anymore. So that's where we found that building little accelerators onto the chip that have very specific purposes, so they could be built very small, because it ends up that compared to a general purpose CPU that has to run everything from all kinds of workloads, a very specific design for something, let's say, that does data encryption. That's a very small engine. We put that small engine onto the chip. Suddenly, you don't have to do the data encryption on those CPU cores anymore. You can do it on the accelerator. And we call it a built-in accelerator, or an accelerator engine. And these accelerator engines are various types. We have actually the largest number of built-in accelerator engines in our 4th generation Xeon that we just launched than any other CPU on the market. And the reason why we put those accelerator engines there is so that you don't have to do the compute that specific computing workload on the CPU cores. So you save power, you actually get much better performance at the same power. So there's just a big benefit to using accelerators. Now, the trick is that you have to spend time architecting these very specific accelerators. But we spent a lot of time deciding on which are the minimal number of accelerators that we need to handle all kinds of computing. And the encryption is actually part of one of our accelerators. And we'll talk about it more later. But no, it's exciting to see how the accelerators can actually give a boost of performance without boosting the power at the same time. So people who are deploying in the data center, companies that are deploying all the e-commerce, whenever you go and shop online, You want your shopping experience to be fast. When I'm looking up books or I'm looking up clothing and buying it online, I want to get that response fast. And those databases are getting bigger and bigger and bigger. The amount of compute is getting bigger and bigger. How do we do that faster and faster without having the data center power bill, and also meeting sustainability goals? So there's so much involved in these accelerators. It's really exciting to be here talking today about what we're doing. And it's really hard to know even where to start, but that's kind of the basic explanation of why accelerators, because that's what's going to get us into the next era of computing, more compute at lower cost, at lower power.
Yeah, no, that's really good stuff. And just to give a garden variety example for everyone out there, like Gary said, when you're shopping online, whether it's, you know, some big store or local store or something like that, you're looking through all the different products. You need to be able to find them quickly. So that's the database size he's talking about, especially if it's a big major player like Amazon, for example, and the number of products they have is just it's unbelievable. But also, once you're finished shopping, like if my wife goes to the Whole Foods all the time, once you're finished shopping and you click that purchase button, you go on to the cart, it all slows down, right? And that's because now you're kicking in security mechanisms, you're kicking in the financial side of the equation, you're going to be connected to banks and so forth. And that's the kind of different workload you're talking about, right? Browsing is one sort of workload, but then actually checking out and giving your money and engaging with these financial institutions, that's a different kind of workload that requires a different kind of processing, right?
That's right, Eric. All these specific workloads require very specialized processing. And encryption and security is becoming more and more prevalent. So it's not still okay to just have security on your one application that you're running. You need security on whenever you're clicking on a URL and you see that little lock, that means you've got a secure connection. That means there's a lot of encryption going on, and you'd be wasting power and wasting time if your general purpose CPUs on the chip were doing that compute. Having these accelerator engines doing the encryption means that you can get many, many more users on the same processor in the cloud. You know, these computers handle many, many users at the same time, and at much less power and much less cost.
Yeah, and if you're rendering, and I'll throw this over to Eve, maybe I was joking earlier about how you'd like hit the enter button and go home for the weekend. I know people who did that for a living because they were doing video productions back in the 1990s. Believe it or not, it's a long time ago. But when you're doing video production and you're trying to run that through the processor, well, to Gary's point, there are lots of different ways that you can architect the process of getting that done. And what you don't want to do is be spinning your wheels. What you don't want to do is be using a suboptimal architecture to process that, because then it takes longer. And to Gary's point, it costs you more, not just in time, but in energy cost. So there are lots of reasons why you want to approach a particular workload with the right architecture. What do you think, Eve?
Yeah, exactly. I was just thinking that in a general way, the complexity of the tip of where you say that we do encryption, we do financial transactions and so on, this puts some more complexity on the architecture. And that means if you want to scale, that puts a burden as well on how you can scale. So businesses have become much larger than in the past, where it, like you said, Gary, they could do it with the traditional multi-purpose CPUs. But if you look at it right now, today, you have, 100 customers, and in 3 months, you have 1 million customers. So to scale up your architecture and your infrastructure, it needs a different approach to be able to follow in these huge volumes, in this huge number of transactions, to build a global online type of businesses. If you see, for example, if you see how ChatGPT, for example, ramped up the number of subscribers to their platform in just a few months' time, I mean, it's insane how they leverage this type of compute in the back end to be able to build that type of business. I think back in the days, you had to go and get a purchase order to order a new server, to tear that up and make it available to do your compute. So that gives a lot of possibilities as well to innovation, that companies can do more with less for these days. And like you said, with the sustainable goals in the back of our mind, that's an important one as well, why you have to use less energy to do all the number crunching.
Yeah, and efficiency is always the name of the game, right? So you're always trying to become more efficient. And Gary, real quick, I'll just throw this one over to you. we all know from experience, when you got a faster computer, you get used to that speed immediately. And if you go back to an older computer, you're going to be a very unhappy person. I mean, I remember watching some meme. I saw a meme that said, if you're about to date someone, put them on a computer with a very slow internet connection, just so you know who you're dealing with. It was kind of a joke. But the point is, we get used to it immediately, and then you must have it, right?
That's right. That's right. And you're both making a great point, Eve and Eric. Businesses are trying to scale, and they're trying to be very efficient. And one of the things I wanted to point out about businesses scaling and getting that efficiency is AI is becoming more prevalent in terms of scaling businesses, getting more efficiency, running AI programs. But there's two kinds of AI. There's the kind of AI that you're going to need when you're running servers doing ChatGPT 24/7. Right? But there's the kind of AI that most businesses actually are trying to run, which is a part-time kind of AI, not full-time. And so what do you do when you need to have data centers and you want cloud computing to be faster and faster and faster, but you're not doing AI all the time. You're doing it some of the time. It's a mix of workloads. So whether you're talking about like industrial kinds of applications, or you're talking about e-commerce or something, there's AI running, but there's also a lot of storage server and data retrieval and databases and other things. That's why we've made the 4th gen Xeon processor. We've put very specific acceleration for AI so that in this generation, we're getting up to something like 8x the performance of AI at the same power.
Wow.
Because people are having to run a mix of workloads. But you talked about specific kinds of GPUs and AI acceleration. So you have these kinds of bolt-on, add-on processors that if your server had to be running 24/7 AI, like training new models or doing that kind of high-performance AI 24/7, we have also kind of those kinds of processors that are discrete accelerators that are bolted on, that are added on hardware. But most of the time, actually, people are just looking to the processor that they already have, the Intel Xeon processor in the server, to do more and more AI in less and less time and less power. And so that's why we've added this thing called advanced matrix extensions, which is one of the accelerators on the chip to increase the performance of AI drastically in this generation. Just because the insatiable desire, I mean, everybody now, something like half the businesses we've seen are now using AI for more efficiency.
That's amazing. It is on the rise. There's no doubt about it. And to Eve's point, I've never seen an uptake of a product like what we just saw with ChatGPT. And just to sort of dissuade some of the rumor mongering about ChatGPT, it is a large language model. So some of the bad stories you've heard are because people weren't using the tool properly. It's not meant to be portraying a sentient being. It's meant to be a large language model. But folks, don't touch that dial. We're talking with Gary Brown from Intel and Eve Melkers. We'll be right back. You are listening to Inside Analysis.
This episode of Inside Analysis has been sponsored by Intel. Accelerate your business with the new Xeon processors.
Welcome back to Inside Analysis. Here's your host, Eric Kavanaugh.
Take us to the future.
All right, folks. Take us to the future indeed. It's so exciting talking about processors being rolled out because they are the brains of the computer. And they're just amazing stuff. It blows my mind when I get down to brass tacks and really get into the chip architecture and wafers and so forth. And we may get to that in the show, but there's a lot to cover. But I did want to bring in our good buddy Gary Brown again from Intel and our buddy Eve Molkers to talk about CPUs versus GPUs versus these new processors, the Xeon processors. Because I remember when probably 7-8 years ago in the data business, someone figured out that GPUs could be used for massive data processing, right? Typically, you would use the CPU to do that. And GPUs got very popular because of gamers, because they're good for graphics. And of course, graphics, it's so intense, right? Gamers do not want a slow computer because it pretty much ruins the entire experience. It's got to be real time. The bullets have to be flying, all that kind of fun stuff to do gaming. And look how huge gaming has become. It's amazing. But Gary, I wanted to bring you in to talk about the difference between traditional CPUs, multi-purpose, and then the GPUs, and then what you folks are doing with AI and why GPUs aren't always the best idea for AI and that kind of processing. Go ahead, Gary.
Yeah, Eric, this is a great topic. I really love talking about computer architecture, actually, and GPUs versus CPUs. if there hasn't been such an exciting, kind of battle of people's attention, because GPUs, you're right, it was for gaming, it was for the pixel rendering, pixel shading. GPUs are very powerful when it comes to being able to do display processing and pixel processing for getting faster and faster gaming and much better gaming and CG in your games. But because the GPUs became so prevalent, they were available to do other kinds of data processing as well, right? That's what we're talking about.
Right.
And so people use them for all kinds of things. And AI and neural networks, when a number of years ago, around 2010, 11, 12, people were starting to talk about these things called convolutional neural networks, really exciting stuff, and running them on the processors that they had in their gaming machines with these GPUs. Now, but the interesting thing is that the GPUs weren't originally built for doing neural networks, but they do a lot of addition and multiplication, which are the two things you've got to do a lot of when you're doing neural networks. So they were used and adapted really quickly for neural networks, and even still today are being used quite a lot for neural networks. Now at Intel, we're building GPUs and we're launching GPUs and we have them available. But the interesting thing about these neural networks and AI is it's gotten more and more precise and more complex. And with AI, it just needs more and more compute. And so what we've done with Xeon is we've made AI a really, really high profile aspect so that people can get really great performance, really great efficiency with AI. And you don't always need to add on the GPU. The downside of a GPU is that it costs money and it costs power. And so when people today, when they're designing their data centers, and they're all the big companies that have the social networks and e-commerce and are in the cloud services for all kinds of things, they're very sensitive about power and cost. And you have to make decisions between, like, for what workloads and for what applications you really do need the power and performance of a GPU at the cost of your electric bill. Mm-hmm. Or you could be using a processor where maybe you don't need that. So the GPUs aren't the most efficient for AI. What we've been able to do is design more efficient processors to be able to do AI with great performance per watt of power or per dollar of cost. Mm-hmm. But GPUs still, they're the sledgehammer because they give you just so much performance when you add on a very powerful GPU. And that's why Intel's already working on that and deploying it for things like supercomputing, for weather simulation. If you're simulating the weather of the Earth, you're not going to just use your desktop or tablet or cell phone. You're going to need the most powerful computer on the planet, which has a lot of CPUs, a lot of Xeon CPUs, and the Intel GPUs as well. So sometimes you need both. If you're doing something like weather simulation or building aircraft, you need to simulate the air and the motion of all the particles of air around the aircraft or spacecraft, to be able to make sure that it flows efficiently. So fluid dynamics, there's just so many, drug discovery, pharmaceuticals, how many different ways proteins and water molecules can bond and all of that. I'm not an expert on that at all, but it just takes loads and loads of compute to be able to do that. And sometimes those GPUs come in convenience, but they also cost in terms of power and in terms of power and dollars. So there's the trade-off.
That's exactly right. That's a really good point. And as you think about why you would want different kinds of processors and different accelerators for different workloads, I mean, we could make any number of different analogies, but one would be automobiles, right? Like, I could put a really big engine in my Mazda Miata and it's still not going to be good for hauling lumber around because it's a teeny tiny little car. And so these efficiencies really come into play when you understand the nature of the workload, the nature of the processing that's going to be needed to get done, and you optimize for that. And of course, it takes a while, right? It takes a number of months and years to come up with these designs, and you guys have been working on this stuff for quite a while now. So you've seen the different kinds of workloads out there. And to your point, some of this is going to be in the cloud. Some of this will be for cloud computing, but some of it will be for on-prem too. It just depends upon the needs of the customer. And that's something you guys have a lot of experience in, right, Gary?
That's right. So I'm going to pick out an example just at random here. When you're storing a lot of data, so when you have large files and you need to store them, we all know about zip. You zip the file, right? Well, in the network and on storage devices, it's also doing that kind of data compression. So you have to have data compression. And those data compression algorithms cost a lot in terms of compute. we've been able to put them into an accelerator to be able to offload from all the different general purpose CPU cores on the chip and run it on a dedicated acceleration engine. And we can also do encryption of the data at the same time. So encrypting the data, compressing the data, doing it in a very large, bulky kind of way for the large amount of data that's on a network, or that computers in a data center have to be able to, kind of move data around. Imagine when filmmakers are out there making movies and they're storing their data and retrieving their data. There's a lot of that encryption and compression of the data and decompression of the data going on behind the scenes in the server. And we have quick assist technology. So the quick assist technology is one of those accelerators that is dedicated to doing pretty much just that, the compression and the encryption. And it works really great because when you turn on that quick assist technology, you're getting multiple times more performance at very similar amount of power than you would have been, consuming by the chip. And that's what we found with our new 4th Gen Xeon. We're getting great results using this quick assist technology as an accelerator on the chip. In fact, one fun fact about Intel, we used to have quick assist technology as an add-on card in the system. And so we've moved it onto the chip. And so now we're getting great results. You don't need to add in an add-on card anymore because we're getting that acceleration. So accelerators are able to give you better performance, much better efficiency when you use them for the applications that typically tend to matter. And what we've seen is a lot of these applications like encryption, compression, AI, they're very prevalent. They're growing a lot, and those are the things that we've, attacked directly with the putting these built-in accelerators on the chip.
Yeah, and you know what's so cool here? You just got me all excited again. He's talking about the old days, right? When you put cards in, you buy your big PC, and you have all these slots that you can put your specialized cards in. And what they've done over the years is figured out, okay, well, this card is doing a very specific workload. And in the manufacturing world, in the lab, they can take that workload and miniaturize it and then put it on the chip. So now you don't need a separate card anymore. They figured out the flow of the data and the flow of the electricity basically and said, okay, let's put that onto a teeny tiny little chip. And now that's your accelerators, right? So you're saving space. Obviously, you're saving manufacturing time and cost and instability and all these different things by innovating, by understanding the nature of the workload and then morphing that into a new form factor on the chip. Eve, I get all excited about that stuff, and you've kind of watched this happen over the years too. It's very cool, and you just like look at one of your old desktops. I'm a geek. I have computers lying around here from the old days. You like, look at that beast. Like compared to the new ones, it's like there's no comparison. But what do you think about the process of understanding the workflow and then baking it into a chip? That's cool stuff, right, Eve?
Yeah, I'm just following what you were saying, Eric. In the beginning, everything had a special slot to tackle that specific workload, and I think with the miniaturization and production processes, where you can put more in a circuit, and they became more miniaturized, and learning from what you typically have and put that on the chip itself. I mean, on the CPU or the central processing unit, put that on, and do not have a need to outsource it to specific other processors, which were much farther away from the CPU or much even in another place and had to travel over the network and so on. This is an insane evolution if you see what we can do right now. You talked about the old PCs that are lying around. If you see what we now can do with our phones, it's amazing. And I think we're still only at the beginning of how far we can go, even with the number crunching, with all the AI coming up and the specific workloads and optimization, what is coming up.
Yeah, well, and you get into the power side of the equation and the speed side. And just real quick, Gary, I'll throw it over to you. When it's a separate card, obviously the instructions have to flow through the motherboard over to the card, into the card, do its thing, and then back over to the processor. I mean, that's taking time, it's taking energy, and that hurts efficiency, right? So when you miniaturize it and put it onto the chip, you save in all kinds of very interesting and very compelling ways, right, Gary?
Yeah, Eric and Eve, this is a very good point that the distance, how further away your processing is, the fact that you have to, if you're adding in a card or adding in some specialized hardware that's off the chip, you're not only sending the data off the chip, which takes more time, takes more effort, takes more energy, takes more power, but you also have to set up that connection. So there's a lot of overhead, actually. You have to be able to communicate off chip. So to put a built-in accelerator into the CPU what we've actually done is minimized and really reduced the amount of overhead in terms of time and latency, and also in terms of power and speed that you can get when you do whatever kind of processing. So take, for example, we have another accelerator that's very efficient on moving data around, data streaming accelerator, the Intel DSA. And what this does is it enables you to not have to use the embedded CPUs to calculate where in memory you're trying to store lots of data and move lots of data and copy lots of data. There's a lot of data operations going on in every application all the time. You just want to minimize how much of the power and performance of the CPUs you're using on the chip. And now we've got a little accelerator that's just doing that all the time, the data streaming accelerator, to make sure that data is moving around really fast. But not having to go off chip, we've actually built a special architecture for putting these accelerators really tightly connected to the embedded CPUs, so that when you have to offload some particular workload, you can do that in a really efficient way, and minimizing just the sheer overhead, which is huge compared to having off-chip hardware. So yeah, there's a big benefit to that, and takes a lot of work from the architects who've slaved away, building this new chip. But the benefit has been incredible in terms of performance and power efficiency.
Well, right, and you're also waiting on things, right? And so and you can think in the working world out there, if you are a manager and you're waiting on supplies to come in and they don't come in on time, well, then you can't do a particular job. But it's the same thing in the computer with the processor. If there's some process you have to wait for, you see this a lot with the network, right? When the network is slow, it causes all kinds of problems. I remember in the Hadoop days, which we've talked about quite a bit, it was a very interesting approach to solving for a particular problem, but you relied on the network so much, and the network becomes the bottleneck, right? So there are always all these bottlenecks that are on the board and the architecture of the application of the design or whatever, and you want to be able to solve for the most important ones that are going to bring the greatest amount of value. And that's what you folks have done by putting these accelerators right onto the chip, because the actual distance really matters. I mean, it's funny and fun to think that the speed of light comes into play here, but it really does. And that sort of disjointed old approach is really slow, and people don't like that. Real quick, your thoughts, Gary, before this next break. You got 60 seconds.
Yeah, no, you're exactly right. Minimizing the amount of time that it takes for everything from ordering things online to things, moving data in the network to, kind of the embedded systems that are at the edge computing on premise at retail stores. It all matters. And we're optimizing on all of it with built-in accelerator technology with our accelerator engines. So it's really exciting stuff.
Yeah, and the edge computing stuff, we should probably get into that in the next segment a little bit, because it is such a big deal, right? And so we went from, just real quick, I'll give our audience the history of the mainframe. Remember the mainframe, folks? And there was some famous person that said there were only going to be 6 computers in the world, and those are the mainframes. And then some smart person figured out recently, yeah, maybe he wasn't wrong, when you've got Amazon and Google and Microsoft, and those are the new sort of supercomputers, if you will. So it's not that far off. But then we went to the whole client server days. That was very familiar for people in the industry, in the working world, especially in the 90s and the aughts. And now we're entering this next phase. And edge computing is a really interesting concept, because edge is wherever you are. Edge could be at the shopping mall. Edge is on your phone. Technically, your phone is an edge device. There are issues with the routers that come into play and what they can do. So the point is, with the edge computing world, it's going to get bigger and bigger and bigger, and that is a form factor in and of itself. And it also brings in all sorts of very interesting architectural considerations for the workflow and the process, because you're going to want to process some data at the edge and then just send the signal back over the wire. You don't want to send all that data over the wire back and forth. It's too costly and too slow. So there are lots of different things that come into mind here. And the fact that Intel has thought through all these accelerators, I think is very, very clever. And it's going to be applicable to all these different industries. But folks, don't touch that dial. I'll be right back. You are listening to Inside Analysis.
Take us to the future.
Welcome back to Inside Analysis. Here's your host, Eric Kavanaugh.
All right, folks, back here on Inside Analysis. What a fascinating conversation today. We're very thankful to have our good buddy Eve Mulkers from 7W Data and Gary Brown from Intel talking all about the new Intel Xeon processors with these accelerators. And before the break, I was getting all excited about edge computing and the edge. And of course, the edge has to communicate to the data center and then out to, maybe an on-prem data center, for example, and to your device or whatever. But there's a lot of different characteristics that come into edge computing. One, different power profile. Sometimes you don't have a lot of energy out there on the edge. Different form factor. You can have very small little Raspberry Pis can be out there on the edge doing stuff. But Intel has thought through all that stuff. So Gary, tell us how you've optimized for this whole sort of panoply of options out there.
Yeah, no, it's great to be talking about the edge computing. We've heard about the term IoT, Internet of Things, for many, many years. But edge computing is very serious and a big growing industry. Intel's really going after it in a big way. There's industrial manufacturing where product defects need to be discovered really quickly. Computers and cameras are being used to do those make defect detections. With retail, we've seen some automated retail stores that are able to get frictionless checkout. So you can grab something off the shelf, and through the use of technology, you can get charged to your credit card without having to walk through a checkout stand and things like that. So there's, retail and industrial manufacturing, physical security, at an airport. There's a ton of technology behind the scenes, but has to be super on-premise, low cost, low power, miniature servers that are still just almost as powerful as the servers in the cloud, but very, very low cost and small form factor. So that, there's different needs for the kind of computer you're putting in a retail store than the one that, Amazon and Microsoft are putting in the cloud. So for those kinds of things, we're still using the Intel Xeon technology. We're just using a different flavor of the chip that has fewer CPU cores, lower power profile, and gives you the performance that you need for those kinds of edge computing applications. And then as you scale up to the Xeon processors that are much higher performance, still you need power efficiency like we've been talking about here. But it's a much different performance power tuning that you're dialing in when you're talking about edge computing versus the network versus the cloud. So the same Xeon processors, we have the smaller ones with the larger ones, and it's interesting the way that we can adapt the same technology and scale it to be able to solve some of those problems for edge computing. I mean, even drones have processors in them that take movies and can follow you and have some AI technology that filmmakers are using drones heavily these days for trying to reproduce a shot. And so you have to program the drone, and the drone has processors inside. So a lot of different edge applications.
It's amazing.
It's really cool stuff.
Well, so, I mean, just to talk very quickly about cool drone use cases, I mean, in the insurance business, when hurricanes come in or tornadoes or whatever, I heard a stat from an expert in the field who said their cost per building to inspect went from like $2,000 down to $100 or something like that, because the drone can just fly overhead and take all these pictures, and that's all the person was going to do with their camera is climb up on a ladder, risk his or her life, and take pictures. So this is just one tiny example of how these technologies are dramatically changing what you can do. And when you can do the processing at the edge, that's some pretty exciting stuff, because you can do a certain amount of processing, let's say in an oil rig, and figure out, hey, this is a serious problem as opposed to a minor problem. Now we have to fly a helicopter out there to work on something. All these kinds of use cases come into play. And when you can leverage this array of processing technologies, you can solve the problems in a efficient and cost-effective manner, right, Eve?
Yeah, exactly. That's just the top of the iceberg, what we can do with technology and use it in a different way. Think with the evolution of the 5G network as well. But you brought up a great point, and I was just thinking about what Gary was saying about the Intel Xeon. You have different flavors, and you have the small one and you have the big one, sort of say, where you can use the small Xeon in your edge devices. But does that mean as well that you kind of can do the same type of processing or architecture on the edge as you do in the central data center, and that your architecture in total and your programming of your applications becomes simpler than opposed to where you had to do a different type of programming in the IoT devices compared to what you are doing on the central crunching of the numbers?
Yeah, no, that's a great question, Yves. The question is, how does the architecture change for edge computing versus the network versus the data center? With Xeon, you're able to still take advantage of accelerators that are on the chip for different applications. It just depends on what application. So if I'm thinking about industrial manufacturing and you have cameras that are connected to, even sometimes the cameras, inside the cameras themselves, you'll have processors, but typically connected to a small form factor server with a flavor of the Xeon that's meant for edge computing, you get some of the same kinds of things. But it's kind of like if you buy a car, you buy kind of the high-end model with bigger engine, you buy the smaller, sportier model, it's kind of having those different kinds of ways in which you look at the technology. But it's interesting to be able to compare and contrast how your processor would perform at the edge versus in the network. And the way that we measure performance today is just really, really different than the way that we did in the past. But that's a whole nother story.
Well, I was going to say, this all comes in handy. And I think for our podcast bonus segment, we can get into this topic that really excites me, which is observability. And the observability of systems and of machines talking to each other, learning which architecture is better than some other architecture. That's all best practice stuff. And it's happening right now. There are just all these different companies coming out that are focused on what's called observability. And that basically just means monitoring this system, monitoring that system, getting very fine-grained details on how the processor is affected, how the storage engine is affected, how much time it takes to do things, how hot things are, the temperature of things, we talked about IoT, Internet of Things. I'm here in Pittsburgh, Pennsylvania. East Palestine is like 40 miles over that way. If there were sensors on that train that would give you a reading on the heat of the bearings and the wheels, that probably would not have happened. And so, but again, these are issues that have to be dealt with across the spectrum of an industry, right? So my point being, we're learning tremendous amounts right now about how these machines talk to each other, how taxing they are, how much energy you use from this processor to that processor. All that gets baked into these decisions that are being made, and we're going to see worlds of efficiency gained. I'll throw it over to Gary to comment on. It's very exciting because you almost don't realize how cool something is until it arrives and you compare it to what you had before, and you realize, wow, we were wasting a lot of time and energy doing things that way, whereas now with this new set of processors, it's really going to improve efficiencies across the board, right, Gary?
Yeah, no, I think there's going to be really cool applications that make use of efficiency. And one of the ways I think about efficiency when it comes to these kinds of processors in the cloud and in edge computing or in IoT kind of devices is that people are figuring out what actual compute you need to do at the edge. Right. And then you send data to the network, and in the cloud, you can do the rest of your compute. So take, for example, a really easy example would be in a camera, you can actually detect things, detect an anomaly or detect which product somebody's grabbing off the shelf and do that detection, but then send that image into the network, and then you could do more analysis on it and say, oh, it's this actual product with it costs this, look it up in the database, do all the big number crunching in the cloud, but do some of the stuff at the edge that you need to do at the edge. And so a lot of these applications are actually not running in one place or the other, but everywhere. So the applications are containerized, so you're running some things at the edge, then moving some data to the network, running it in the network. So a lot of times the connection to the network itself has to be fast, the cloud has to be fast, and in the edge, you're able to do a lot of things just because of the fact that it's on-premise and very low latency, very expedient.
Yeah, this is just fantastic stuff. We have one segment coming up next, folks, but if you're listening to this and thinking, I want to know more, just go to your computer, type in Intel Xeon, Xeon processor, and I guarantee you're going to find all kinds of information about it. And it's not just for the data center. It's not just for the cloud. It could be for personal use. There are all kinds of different, I've already seen the different companies offering servers using these new Xeon processors. I'll give a last comment for 1 minute to Yves Mulkers. How excited are you about all the new possibilities here, Yves?
Yeah, I don't have to say it anymore. I'm pretty excited on what you can do right now and the possibilities. And definitely, I mean, what we've learned of the typical workloads we had to tackle, and now having an optimized chipset for that. It's just the start of so many new possibilities, and really making technology again an enabler for exciting and inspiring business models.
Yeah, and we're learning new ways to do things. I mean, that's the cool thing. I think we'll talk in this final podcast bonus segment here about the difference between processors and computers, and why clock speed isn't always the most important thing. And we'll figure some of that stuff out. But we're learning every day. And in the lab, they're learning as well. And they're figuring out what else they can miniaturize to put on these chips to optimize the speed of transactions, the security of transactions, the variability of business models. All this is good stuff for business folks like us. And folks, you've been listening to Inside Analysis. All right, folks, time for the podcast bonus segment here on a fantastic show. We're talking to Gary Brown from Intel and Eve Molkers of 7W Data, introducing Accelerated by Intel Xeon. It's great architectural stuff. And we wanted to talk about clock speeds and like megahertz and gigahertz and all that stuff, because you used to always just look at, okay, how fast is the processor? Is this going to be fast enough for my needs? Because I do a lot of video editing or whatever. But now with these accelerators, it's a whole different ballgame, because you've sort of abstracted away some of the more challenging components of the processing and separated that out to have more of a separation of concerns, as we say in the industry sometimes. Can you explain what that means? And you have a fun example, as I recall. Go ahead.
Yeah, no, Eric, this is a cool topic, because when I started out in the industry in my career, computers were simple, and you could, microprocessors were all kind of based on very similar kinds of architecture. And you could look at one CPU and say, oh, this is 100 megahertz, this is 200 megahertz, so this is about 2 times as fast. But things have gotten complicated with superscalar processors and the way CPUs are built, and now embedded engines are being put. And you have to, I mean, it's just such a complex device. I think these CPUs today are the most complex microprocessor devices that are built today. And the way that we compare them, it's not as simple anymore. So, for example, you look at a 2 gigahertz processor and you look at a 2.2 gigahertz processor and you say, oh, that must be a little bit faster. But the question always comes up, what are you trying to do with the processor?
Right.
And when you actually measure, and what's really interesting about what we do in our labs when we're measuring the performance on real life applications, whether it's AI or storage or networking, databases, e-commerce, all these kinds of things, you actually look at the real performance of the real workload or application, and then you look at the processor and you say, wait a minute, this one that was 2 gigahertz is actually faster than the 2.2 gigahertz one. Why is that? If we turn up the clock speed, shouldn't it be faster?
Right.
But there's a reason why it's not. And one way to think about it is, think about a kid on the playground in a sandbox. And he or she the little kid is scooping up the sand really fast into the bucket. And you can actually clock how fast the kid is scooping up the sand, maybe 10 scoops per minute or 50 scoops per minute. Then you bring in the big Caterpillar excavator that digs up maybe 2 or 3 tons of dirt. But it can't do it 10 times per minute. It can't do it 50 times. It only does it 1 time every 5 minutes. So, the excavator is certainly much, much slower than the little kid in the sandbox. But what if you had 50 tons of dirt you were trying to move on a big project? Are you going to get the little kid to do it, or are you going to get the excavator to do it? Well, I mean, the application here is much faster when you're using the excavator, even though when you're just timing the speed of number of excavations per minute, much, much slower. So it's really the amount of work that can get done that is today's kind of equalizer across whether it's a CPU from Intel or another company or a GPU or whatever kind of processor you're trying to compare. What work are you actually able to get done in what amount of time, at what amount of cost, at what amount of power? And it's so much more complex than just, let's just turn up the clock speed and we'll end up with a faster result. Because sometimes the higher clock speed architecture was the one that wasn't able to do as much work per clock cycle.
Interesting.
So that's, what is the instruction set of the clock? What is the basic stuff that the thing can do? can it do 3 multiplies in one clock cycle? Well, maybe this one over here can, but the other one can't, but the other one's slightly faster, but this one gets more multiplication done. So like how you compare processors today is a bit more sophisticated, and it comes right down to what job can it get done and how fast and with what power and cost. And those are the kind of questions that we try to answer. And this is exactly why we develop these built-in accelerators, to get the kind of work that people are wanting to get done more in their cloud, in the network, and in the data, in the on-premise IoT or edge computing. But with this acceleration, now they can get much better results. And it's somewhat more loosely affiliated with the clock speed. It's not directly affiliated with the clock speed anymore, because we've changed it all up with these accelerator engines.
Yeah, it's another layer of abstraction, and it really expands out the different permutations and different ways you can do things. And, Eve, I'll close with you. In the data world, in the AI world, well, what does AI need? It needs a lot of data. You have to train these models on data. These large language models, we talked about ChatGPT, was trained on a massive corpus of data. I looked into it too, and it is bewildering what they've done. I mean, in some senses, one of the things they did was to turn every word and every letter into a numeric value, so you can do statistical analysis on how these all things come together. It's really quite fascinating. But just real quick, 1 minute left, Eve. The volume of data now is so massive too. So you want to be able to handle that, not just with software that you purchase, but with these new chips and these new accelerators. It's a really, really big deal on handling the volume of data, right, Eve, real quick?
Yeah, exactly. You mentioned the number of parameters what you have on the big AI models, and it's exactly that. Before, because we didn't have the technology, you had to sample it, and it was not really representative for the real world as such. Now that we have the technology, you can do that even in real time. Look at that data, look at the insights. So we're coming very close to real-time AI, and that's where you get the competitive advantage and the real new type of business models, and that fraction of a second, what we mentioned before, if you do your online shopping and kind of get the glimpse and well, where a millisecond is really very important on your revenue of your business. And I think that's what we see in the evolution and the possibilities, what we're doing. And data has a different way of how it moves through systems. And that's very important, what we learned from the past, and what you can do it and how you can do that now with the new architecture of the Intel Xeon.
Yeah, and folks, if your website runs just 1 second faster, you're going to sell more stuff, I promise. And with that, we'll bid you farewell. Big thanks to Gary Brown from Intel and Eve Malkers of 7W Data. You've been listening to Inside Analysis.